So we're going to start up the Logic Lab this week, but I did not manage to book the rooms yet. So what we're going to do for today, so we're going to try the following schedule. We were not able to, unfortunately, the doodle poll results were like fairly even across the week, and we can't run every session that was possible. So what we're going to try is the following. If you are desperate to have Logic Lab time and you can't make either of these times, get in touch with me and we'll try to figure something out. For now, let's try this. So we'll have Mondays 3 to 5, Fridays 11 to 1. Today, we're going to do a kind of informal, just come to my office. So my office is at the Jackman Humanities Building, room 538. It's on the 5th floor. Just take a left off the elevators. And just come if you're having any kind of, this is, I know I said for my office hours, I prefer not to like teach you logic one-on-one. It's like any other logic, like any other issue, you're welcome at my office hours. This, you're welcome to come just help if you just like want help with logic. So any issue whatsoever, you're welcome to come to my office today, 3 to 5. We'll talk about it. We'll talk about setting, if you're still having trouble setting up Logic 2010, we can work on that. Literally any issue that is course. Actually, maybe if you're having like an existential thing, save that for the office hours, so we can do logic at the Logic Lab. So is that all right? Yeah? Okay. So exercise 1 is now posted. The first weekly exercise is up on Quarkus. So the questions that you'll be doing are up on Quarkus. Now you'll be doing these on Logic 2010. So if you haven't got that installed yet, now would be an excellent time to get it installed. Yeah? So check the assignments section where there's a list of, so in general what I'll do is I'll post which questions are the assignment in the assignments section. But there's nothing that you submit on Quarkus. You submit it via Logic 2010. Yeah? And you have to both, so what I'm going to do, in this class, I'll show you some of the Logic 2010 stuff. So there are 3 sort of things you'll have to do on Logic 2010 to complete this exercise. I'll show you 2 of them today and the last one on Wednesday. But the crucial thing to remember is that you need to both save your work and submit it. So when I'm checking to see whether you did these assignments, I'm going to the Logic 2010 website that tells me whether you've completed it or not. Yeah? Or how many of them you have completed. So you have to submit, you have to have internet access, you have to submit your answers. And then I can see, going to the Logic 2010 website, that you've done it. Yeah? And you can go to the Logic 2010 website to check that you've successfully submitted it. So if you want to confirm that your thing has been submitted, go to the Logic 2010 website. There's a link on Quarkus. Hopefully that's clear. Again, I'll show you sort of like the basics of Logic 2010 in this class if that is still mildly abstract or worrying. Is that all right? Okay, so there's probably more questions in this exercise than you strictly speaking need to do in order to understand the tasks that you're facing this week. Mostly, and you might find that so it's really bad pedagogy, it's bad teaching theory to like give people easy questions at the beginning of the course and then harder questions because you're like, this class is easy, and then it gets harder as you go along. But the skills that we're learning at the very beginning here are so crucial. They're so foundational to everything else that we're going to be doing that I want to do this kind of slowly at the beginning. So just a heads up, if you're doing these exercises and you think this is trivial, therefore the class is trivial, that's a bad inference, okay? So, mostly what I want to do is make sure everybody's up to speed on using Logic 2010, and furthermore kind of gets the foundational skills that we're doing this week in order that you're well set up for the rest of the course. I promise it'll get harder, if that makes you feel better. All right, okay. So here are the questions that you're going to do. Don't frantically write this down because it's on the website. So there's quite a few of them, but you'll see once you get into them, they're fairly trivial to do. Like the parsing ones are utterly trivial once you get the skill. The symbolization, mildly harder. The derivations, the first 4 derivations are likewise going to look fairly trivial. And I'll actually show you how to do the first couple of these questions. So this is not going to be a very challenging exercise. Any questions about that? Worries? Do you just want to express anxiety? Okay. All right. Okay, so let's get into logic then. So we're doing sentential logic. The basic unit of sentential logic is a sentence, a specific kind of sentence, a proposition, as we said, a sentence which says something that can be true or false. And we're going to symbolize, we're going to use capital letters to symbolize these sentences, these propositions. We're going to use the letters P through Z. Hey, why are we using those specific letters instead of some other letters? Kind of no reason, which is going to be a refrain. There's going to be lots of questions in this class. Why is it that specifically? Kind of no reason, kind of arbitrary convention, but just roll with it. The actual reason is in more advanced logic, you sometimes use the letters A to O for other things. So, but the real answer is for reasons that don't feature in this class. So P to Z are going to be our sentences. And every atomic sentence can be assigned a truth value. A truth value just means that we're saying that it's true or false, and we're going to assign them the letters, basically a T or an F. And we're going to assume that every atomic sentence has a truth value and that there are only two, which is a kind of weird assumption, right? We talked last time about vagueness, where maybe it's true, maybe it's sort of in between true and false. We're not doing any, recall, we're not doing any of that. It's true or it's false. There's only two. There are also more advanced logics where you do things like both true and false, neither true nor false. We're not doing that. Okay. And please, as a note, don't use ones and zeros for this. I know comp sci people often use ones and zeros to play these roles. Please don't do that. Well, I say please. You could do it if you want. We're just going to mark it wrong. So if you help yourself, you'll help bring down the average. But we're going to mark that as incorrect. OK? OK, so fair warning. Use T and F. Don't use ones and zeros. OK. OK, so these atomic sentences are the basic element of propositional logic. More complex sentences can be built up out of these atomic sentences using what are called connectives. And we're gonna do the basic skills of logic using just two connectives. There's a bunch of them that we're not gonna deal with just yet. We're gonna introduce them after you've got the basic skills. We're gonna introduce the rest of the connectives. But it's probably simpler for you to learn how to do things like symbolization and parsing and derivations with just these two basic connectives. So, which are negation and conditionals. So we'll introduce those now and show you what you can do with them. Right, so again, by convention, the sign we'll use for negation is the tilde, this little squiggle. It's sometimes also written as a line, like a horizontal line with a downward stroke, but this is what we're gonna use, please use this. And the negation is the easiest connective. It's also bizarrely not, it doesn't make sense to call it a connective because it doesn't connect anything. It's what they call a one-place connective, which is a hilarious thing for logicians to say, but nonetheless, the negation is easy. It's just whatever the truth value of a sentence, adding a negation makes it the opposite. So if the sentence Q has the truth value true, then not Q, that tilde Q is read as not Q, has the truth value of F. And this is just exactly how it works in natural language. Natural language is the stuff coming out of my mouth right now that you grew up speaking. Natural language is anything except artificial languages like logic. So logic is an artificial language. Natural language is what we all speak all the time. So if I'm wearing shoes, if that sentence is true, it is, look, shoes. So I am wearing shoes is true, then I am not wearing shoes is false. I know, we're getting deep, deep into the complexities of logic right now. All right, so negation is easy, yeah? Negation is the simplest one. That's why we start with it. Conditional is weird and confusing, but nonetheless, we can get this. So the symbol for conditional is the arrow. You might also sometimes see it written as the sideways horseshoe. Don't do that. We're going to use the arrow. And the conditional is a connective in the sense that you could put together two sentences, right? So you've got P, and if a sentence P that says something about the world, it's true or false, and a sentence Q that says something about the world, that's true or false. You can put them together with a conditional to make a more complex sentence, what we call a molecular sentence. Yeah? So, so just quickly going to show you the truth tables for this. This is like if P is true, then not P is false. If P is false, then not P is true, right? Simple, we've got that. Okay, so here's the conditional, which is like a little odd. It's a little bit odd. So these are the values for P and Q. So if P is true and Q is true, then the molecular sentence, if P then Q, is true. Right? So there's a truth value for the parts of the sentence, and then there's a truth value for the molecular sentence that is the combination of the two. Yeah? So the first two should make perfect sense. If P is true and Q is true, then the whole thing is true. Say, if I'm wearing shoes, then my feet are dry, and I'm wearing shoes and my feet are dry, then that conditional is true. And if you say, if I'm wearing shoes and my feet are dry, and I'm wearing shoes but my feet are wet, then that if-then statement is false, right? Okay. Now these other two, in other classes I spend like an hour explaining why this is weird and bizarre. Basically, anytime the first part of the conditional is false, we judge the whole conditional to be true. And that's not how you use the words if-then. It's just not. Why is it like that? Well, there's kind of a limited number of ways to map. So this is what these connectors are what's called truth functions. It's a function that maps inputs to outputs, right? So if you have these are the inputs, then these are the outputs. And you can see if there's only two inputs, there's only like 16 possible mappings, right, of inputs to outputs. And this is the one that most closely matches what you mean by if-then. Nothing else even closely approximates it, so this is what they did. To get to actually how we use the words if-then, you have to talk about possible worlds and similarity amongst possible worlds. It's really weird. It's not truth functional, and so we're not going to do any of that. We're going to simplify this for ourselves and treat this as though it's what people meant by if-then. Okay, so sorry, I made that more complex by like suggesting it's more complex. I could have just breezed over it and you would have gone, oh yeah, sure. That's what that means. Okay, so far we've got two ways of building up molecular sentences, complex sentences, from simple sentences. You can add a negation, or you can put them together into a conditional. So we've just got two ways. We've got atomic sentences and two methods of building up more complex sentences from those atomic sentences. Should be straightforward, yeah? And then you can do that, you can iterate that, right? So these molecular sentences can themselves be made more complex by either putting in a negation on it or making them into conditionals. Let's see that. Quickly, a note on the textbook. So the Terry Parsing textbooks that we're working with here uses the square and the circle as kind of variables for propositions. So this is the way the Parsons textbook gives the rules for turning an atomic sentence or a molecular sentence into a more complex sentence. They say if square is a symbolic sentence, so is not square. I'm going to use P and Q mostly. I hope you can just sort of get that I don't just mean P and Q. I mean any of possible sentence. Is that okay? Mostly I'm doing that because in modal, in a more fancy type of logic, the square means something specific, and it will be confusing if you see that again. Anyway, so is that okay? So when I'm saying P and Q, very often I'm meaning in the context of showing you. So when I show you these truth tables, the Terry text uses a square and a circle here. Nobody's going to get confused by that, right? You're okay with this? Okay. Okay. So recall that every atomic sentence is assigned a truth value, either T or F. So all of the inputs to these truth functional statements get a truth value. And then molecular sentences, the combination of these sentences also get truth values. And the truth value of a molecular sentence is built up out of the truth value of the atomic sentences according to the rules that I just showed you, the truth tables. So let's see that in action. Or wait. So, and of course you can you can build up. So here's a conditional made of two conditionals, right? Get that? It's an iterative process. Okay. Yeah? Yeah. Okay. Okay, so here's where we have to actually learn some skills. This was just giving you the grammar. So far, we've just been giving you the basic grammar of our sentential logic system. Now we're going to start getting into the stuff that you need to know how to do. Parsing is the first thing. So parsing these sentences, the ability to understand what a symbolic sentence is saying. And if you don't get this, you're in deep trouble for the rest of the course. So we're gonna go over this really slowly and carefully. We would read this first sentence is not P, therefore Q. That's a really different sentence than not P, then Q. They come out the mouth in natural language the same. This is one of the ways in which logic helps us disambiguate things. So which one of those do you mean? The placement of the parentheses tells you which one of those you mean. So, okay. So parsing as a skill. Parsing is all about figuring out what the main connective is. So we'll talk a lot about the main connective of a sentence. The main connective is the thing that determines the overall truth value of the molecular sentence. You've got some complex sentence built up out of a bunch of different parts. What's the truth value of that complex sentence? We figure that out by figuring out what the main connective is. The main connective, if we're talking about, we can define this in a kind of constructive way. Recall that there were sort of rules for building up complex sentences out of simpler sentences. The main connective is the last one introduced in the construction of the sentence. You say, well, I didn't see the sentence get constructed, Corey. How do I know what the last one was? You'll see. So here's a sentence. It's not the case that if P, then Q. Okay. So the main connective of this sentence, can you think backwards to how this sentence must have been put together? All you can do is combine two sentences into a conditional or stick a negation on there. So thinking backwards, what's the last thing that must have happened to build this sentence up? Negation, exactly. So in this case, the negation is the main connective in this sentence. The negation sign is where the truth value gets determined. So when we're parsing this is what it looks like in the textbook. We say, okay, so the truth value of the negation sign is given by the truth value of if P, then Q. So whatever the truth value of if P, then Q is determines what the truth value of the negation sign is. And then P and Q determine what the value of that conditional is. Okay, so suppose we do the following. I'm just going to assign these truth values at random, where, again, green means true and red means false. Okay, so suppose that P is true and Q is false. Okay? And if you remember the truth table for this, that was the one case in which the conditional comes out as false, right? So if I say, if I'm wearing shoes, then my feet are dry, and I'm wearing shoes, and my feet are wet, then that conditional is false. Got holes in my shoes or something, okay? So if P is true and Q is false, then that conditional comes out as false, okay? So that's the truth value of that molecular sentence, and then that molecular sentence feeds into the truth value of the even more molecular sentence, not P then, if P then Q, right? So what does negation do? Of course, it just flips the truth value. So now what's the truth value of that negation? It's true. Exactly. Yeah? So the whole thing comes out as true. So if you know that you got holes in your shoes, you can say, well, it's not the case that if I'm wearing shoes, my feet are dry. There's holes in them. Yeah? Okay. So that's parsing. So parsing is taking the complex sentence and breaking it down into its parts. And then you can see how that's important, because that's how you figure out how the truth values get in and get turned into the truth value of the whole thing. So let's do another example. So it's a slightly more complex one. So again, like the truth value of the whole, okay, so the first thing is to try to figure out what the main connective is. What's the last thing that must have happened to this in order to have built up this sentence? It's the middle conditional, right? The middle conditional is the one that's the main connective. Okay. And now we've got two molecular sentences still that can be broken down further. If P, then Q. Pretty obvious what the main connective is there, right? There's only one option. And similar, so it might be less obvious, so you'll have to be careful with the rules. The one on the right, it might be less obvious what the main connective is. Yeah? Still the arrow. It is still the arrow. Yeah. Because if the negation was the main connective, it would be outside of the parentheses. Yeah? Okay? And then there's just one more thing to break down. Obviously, the main connective on this R is R. Or sorry, it was the negation. Okay. Now, randomly assign truth values, and then you can kind of feed those truth values through these truth functions to get the overall truth value of the thing. So, if P and Q are both false, bizarrely, and for reasons that have nothing to do with how language works, that comes out as true. The conditional comes out as true anytime the first thing is false. So if I say, I am a squid, therefore I won an Oscar, logic treats that as true. That's a true thing to have said. I am a squid, therefore I won an Oscar. It doesn't make sense. Don't try to, you could try, but you won't. Okay, so the first thing there, that conditional is going to come out as true because the first thing is false. Yeah? Okay. And then, of course, not R is going to come out as what? False. It's going to come out as false because it flips. Whatever the truth value of R is, the truth value of not R is just the opposite. Yeah? So there we got that. So now we can figure out the truth values of these two things. Once again, on if you feed not R, if not R is the first bit of the conditional, because anytime if the first bit is false, the whole thing is true. Wow, I screwed that up. I was wondering how long it would take me to make an error in the slides, and it was the second example in the first day. And somebody emailed me another error that I made, so there's two in the first day. This is completely wrong. So the second thing should definitely be true because the first thing was false. There we go. Okay. And now the next slide is going to be wrong too, right? The next slide is going to be wrong because I thought that this was false, but this is actually true. And so if the both are true, then it comes out as true. Wow, that's embarrassing. Okay. Once again, so glad I'm immortalizing this all on YouTube so that you can see how clumsy I am. Okay. This is like a modernist logic class with an unreliable narrator. Okay. I'm sorry. Okay. All right. Okay, so we're going to distinguish, when you're doing the parsing tasks on Logic 2010, Logic 2010 doesn't make these weird, clumsy errors, at least. And my TAs are probably better at this stuff than I am, so they won't make these errors on your tests either. So for now, we need to distinguish three things. We need to distinguish official notation, informal notation, and not a well-formed sentence. So a sentence is in official notation if and only if it is an atomic sentence. So just a plain by itself atomic sentence is in official notation, or it can be built up according to these two rules. It's a symbol. It's got just a negation and then the sentence, or bracket, bracket, conditional. Yeah. So that's official notation. And informal notation is just the same. It's official notation, but you don't have to put brackets around the whole thing. So informal, if P then Q, this thing is in informal notation. And you can see, like, it's not, you don't get confused about what that's saying, right? There's no problem about parsing if P then Q. So you could just leave it without the brackets and be in informal notation. But official notation, you'd have to put the brackets around it. Yeah? OK, so you get a bunch of practice on Logic 2010, learning how to identify official, informal, and the other kind of not well-formed. So a sentence is not well-formed if it's not in official notation or informal notation. Sometimes these things look like perfectly good sentences. They look like sentences, but they can't be parsed properly. So, for example, so here's if P then Q then R. That is not a well-formed sentence. It looks like a well-formed sentence, doesn't it? It looks like the kind of thing that we do in logic. But that is an ambiguous sentence in that you cannot assign a unique mapping of the truth values of the elements to the truth values of the whole thing. So let me show you that right now. So there's two different ways of parsing this sentence that sometimes they give the same truth value. So if P, Q, and R are all true, then both ways of parsing this come out as true. But if, for example, we say P is true, or P is false, Q is true, and R is false, then the following thing happens. So if P is false and Q is true, then if P then Q comes out as true. Got it right that time. And then if P then Q is our syntactic unit, right? And then the antecedent is true, but the consequent is false. The first part is true, but the second part is false. That's when the conditional comes out as false. So that whole sentence comes out as false, yeah? And then in this case, the whole thing comes out as true. Because P is false, the antecedent is false, therefore the whole thing is true. So the brackets are what disambiguate. The brackets are what tell us how to do the parsing, right? The brackets tell us how to break these things down into their parts. So the truth of a molecular sentence is based on the truth value of its parts. But you need to know what the parts are. And if you haven't got your brackets well constructed, you don't know what the parts are. Yeah? So this is not a well-formed sentence. It looks like a well-formed sentence, but it's just gobbledygook. In terms of our system, this is just gobbledygook. Here's another example. If they're all false, then it comes out as different truth values. OK. Here's another one. This is just, I just don't even know what, this is just nothing, right? This is just, you can't even begin to parse this, right? People write stuff like this on tests, though. Sometimes you'll get stuff of this sort on tests, and it's just like they're trying to use the negation as a conditional. They'll put two sentences right after each other. This is just, I don't know, this is just nothing. OK? So another case, there's a wide spectrum of not well-formed sentences that are just like, it's just a mass of symbols rather than something that could be parsed such that you can turn it into a truth functional statement. That is, if you feed in truth values, you get just, so the goal is to get it such that you get one and only one truth value out. So if you give truth values to its parts, in any combination of truth values, you should get one and only one truth value for the whole thing. Yeah? That's why it needs to be well-formed. Yeah? OK. So let's explore. This is one of the first things that you're going to have to do in the exercise this week. Let's do some Logic 2010. So if you're doing this on Windows, Logic 2010 does not generate for you a shortcut. You have to like go to the audacity of giving yourself a spot right on the C drive. It's incredible. Anyway, so let's just show you this. So you go to Logic 2010. OK, so I've loaded it all up. You go to Parsing. OK, yeah. You go to Select. And then you pick from, these are all, you're allowed to do any of these problems. But the ones that we'll be doing for this exercise are 1 to 10, I believe. And then you just do the following. So you click one of them. So you select which problem you're going to do. You click OK. Now, you decide whether this thing is in official notation, informal notation, or not well-formed. This one, as we said, just any random atomic sentence is, of course, in official notation. And in this case, you're just done, right? You selected informal official notation, and then you click on check. Oh, it's correct. It tells me up in the right-hand corner. Oh, correct. I've done well. Thank you, Logic 2010. I feel good about myself. All right. And then you save your progress, and then you're going to submit. You submit. You put in your password. You don't have to submit every single time you finish a problem, but it's maybe a good idea so you're never at risk of losing your work. Yeah? Okay. Yeah? Okay, so that's one question. Yeah, yeah.
Is this marked for completion or accuracy?
Well, completion or accuracy, I think they're identical in this case. So it won't let you, so if I do something wrong, and then I go check, it just tells me incorrect. So if I told you that this was an informal notation, it would just be incorrect. And I guess you could submit that. Oh, you can submit that. All right. So you could submit, you could check your work, find that it's incorrect, and submit your incorrect answer, and you won't get the marks for that. So I suppose in principle, those two things can come apart. If you just like go through everyone and give the wrong answer and submit the wrong answers, then you won't get the marks for that. Yeah.
Presumably, it doesn't keep track of how many tries it took you to get to the correct answer. It does not take marks off for that.
It does not take marks off for that. No, I think actually it does show me a report on like how long it took me. It shows me a lot of information about your efforts on these things, but I'm not going to look at that, and it certainly does not factor into your marks. So the only thing your mark is based on these exercises is whether you completed it. It does not depend on how long it took you or how many tries it took you, how many times you pressed the check button. None of that factors in. And by the way, all of these exercises are equally weighted in your final marks. So there's sometimes going to be more or fewer or less, greater or less number of questions, and they're just all going to be equally weighted. Yeah? Okay, let's do one more because this was like a bizarrely easy one. Yeah, okay, I'll save the current. Okay, oh, I got it wrong, boo. Okay, it's okay, I already got my B- in this class. All right, so, okay. Okay, so I'm gonna delete my work on this problem. Okay, so is this in official notation, informal notation, or not well-formed? Informal notation, because what would official notation be? It would have the brackets, right? The brackets would be in official notation. Okay, but I'm not done yet in this case, so we still have to parse this thing. So to parse this thing, basically you just click on the main connective. Click. Bam. Okay, and that's it, because these don't break down anymore. If this was a bigger, more complex sentence, you keep clicking on the main connective until it breaks down into atomic sentences. Yeah? And then you're done. So you say check. Oh, I've done well again. Oh, my life is going great. All right, good. Yeah? Okay, so this is, let's do one more. Like, I mean, it's clear what's up. This is what? This is not well formed. The PQ thing is just nothing. So check, and then you're done. So if it's not well formed, you don't have to do the parsing, but yeah, okay. So we've done 3. Those were 3 of the ones that you have to do for this weekly exercise. I know this is terribly taxing. I swear to God, this is going to get harder. It's going to get much, much harder. Okay. Okay. Is that fairly clear how to operate this thing on this particular task? I don't think there are going to be any parsing problems on your tests. Actually, the parsing is just implicit in everything else we're going to do for the rest of the semester. So for all of the derivations you're going to do, for all of the symbolization you're going to do, you need to know how to do this thing, which is why we're spending extra time and effort on it. Yeah? So we're spending this effort to get this exactly right, because this skill is basically required for everything else that we're going to do. And the skill is actually kind of like the same throughout. So we'll add more connectives. We'll add a bunch of bells and whistles to when we move to predicate logic, multi-place predicate logic. But the parsing stuff basically stays the same throughout the course. Yeah? Okay. Okay, so that was that. Yeah. So we just went through all that. And you gotta click submit. You can click save. It will save your progress to your computer. But if you don't click submit, then it doesn't submit your progress to Logic 2010. And that's how I find out whether you did these problems or not. Yeah? Yeah?
You submit after you do all the problems or per question?
You can do either. You can do either. If you are a nervous type, you can submit every single question. It's going to make you put your password in every time, which is one of the ways that we help you remember your password by constantly getting it. You have to keep entering it over and over again. So you'll have your password. I recommend you make it something easy to type in. But yeah, so the safest way of going about this is to submit after every problem. For these parsing questions, you saw we did 3 in like 30 seconds. It's not like if you lost those 3 questions, you would not have lost a big chunk of your day. Once we get to derivations, these exercises are going to be longer and more complex, and it's kind of a much larger victory to have completed one of them. So you'll probably, I like to submit them just as I finish them, just to let the internet know what a clever fellow I am for having gotten it done. Yeah? Okay, good. Okay. So another kind of central skill we're going to do here is symbolization, okay? So symbolization, turning a natural language sentence into a symbolic sentence. This is how we kind of, like this entire course, like almost this entire course is just a purely formal set of skills. This is the one point at which logic interfaces with humanity as you usually understand it. Symbolization is where you have to both have some grasp on the English language and the logical formalism. So this is how we ground this stuff in like things that you might be familiar with in your life. Right. So symbolizing negation. Again, negation is the simplest one. It's a one-place connective, which is a baffling sentence to me. So suppose that P represents the sentence, the proposition, it is raining. You would represent the sentence, it is not raining, with not P. It is not the case that it is raining, also not P. It failed to rain, not P. Yeah? I think that one's easy enough that like, so these are what we might call stylistic variants, different ways of saying the same thing. Yeah? With negation, again, this is why we start with negation, because it's just so intuitive, so intuitively obvious what you mean when you say negation. Yeah? Okay with that? Yeah? Okay. So conditionals, once again, are trickier. So there's actually no universal agreement on what if-then statements mean, which is slightly embarrassing as a philosopher, you know? Physicists, how's it going? Oh, well, we predicted a particle, and then we found it. Oh, that's great. Chemists, how are you doing? Oh, well, we came up with a cure for cancer. Philosophers, how's it going? Oh, we're having trouble with if-then. It's been a couple of millennia. We're still working on it. I think we're making progress, but it's, you know, we're getting there. We're getting there. Okay. In this class, we're going to simplify it for ourselves. We're going to do this is called the material conditional, but if-then statements. So these words slipped out of me before I meant to use them, but we've got the following. So a conditional has 2 bits, the antecedent or the antecedent, both ways of saying it are fine, and the consequent. The antecedent is the first part of the conditional. If it is raining, then the sidewalk is wet. That's the consequent. Right? So learn those terms, do know those terms. They talk about the parts of the conditional. The antecedent or antecedent and the consequent. Yeah? Okay. So there's a bunch of stylistic variants on the conditional. There's a bunch. This is not exhaustive, but here's a bunch of examples where S represents the sentence, Maria sings, and X, the sentence, Xavier will leave. Javier? Javier? Let's call Javier. If Maria sings, Javier will leave. So notice that the if part comes right before the antecedent. Yeah? Provided that Maria sings, Javier will leave. Assuming that Maria sings, Javier will leave. Given that Maria sings, Javier will leave. In case Maria sings, Javier will leave. On the condition that Maria sings, Javier will leave. I don't know if Javier's a jerk or Maria's a bad singer or what's the situation. It doesn't matter. Okay, so these are all stylistic variants on the conditional. Yeah? And what we're going to do is give you a bunch of sentences that you'll have to represent as logical sentences. So be able to recognize these. Now, there's a couple of wrinkles and complexities here. For example, there's no guarantee, actually there's no reason whatsoever to think that the antecedent comes first in the sentence. Yeah? So Javier will leave if Maria sings. It's the same formalization, right? Javier will leave provided that Maria sings. It's still if S, then X. Yeah? Javier will leave assuming that Maria sings. Javier will leave given that Maria sings. Javier will leave in case Maria sings. Javier will leave on the condition that Maria sings. Okay. So yeah.
Within case,
Yeah.
wouldn't that mean that he's leaving, like, Maria doesn't necessarily have to sing to leave?
Oh, he's leaving like just in case. Just in case. Like it does have that. It does have that connotation. Yeah, it does have that connotation. For our purposes, in case will mean you're indicating a conditional, and in case acts like if. This is one of those points at which, so like we're doing symbolization. We're trying to jam all of the complexities of natural language into our logical system, and some of the edges get cut off. It's a Procrustean bed for those of you who like allusions to Greek mythology. It's a kind of inexact fit in some cases. This is straight out of the textbook. So this particular error wasn't mine. I don't even know if it's an error. Like the in case. So we say Javier will leave, or you could say in the case that Maria sings. Does that make it clearer? We say in the Javier will leave in the case that Maria sings. Yeah. Given that we don't have any way of logically representing the fact of, if it's Javier is going to leave, preventatively in case, the preventatively version of in case, we have no way of logically representing that. So when your task is represent this logically, you've only got a certain number of tools at your disposal. So hopefully it will be clear which of those tools is the appropriate one. And we'll try to design questions on the tests and the exam such that it is clear which of those. There's only a few there's 5 or 6 connectives that we're going to deal with in the whole course. So, yeah. Okay. I'm kind of blowing through the material. I'm going really quickly through this material. I thought there would be more like questions and objections and stuff. So, okay. So, only if. Here's the trick. Okay. So usually, if means, the antecedent of the conditional comes right after if. Usually, in every case except this bloody case, the only if case. Only if flips it around. You say only if Maria sings, Javier will leave. That's if X, then S. Why might that be the case? Okay. Let's look at the truth tables for these, and hopefully that will be clearer. So if Maria sings, Javier will leave. Well, in that case, if Maria sings and Javier will leave, then that conditional is true, right? if Maria sings and Javier stays, then that conditional was false, right? So that's the if-then. That's the normal way of doing the conditional. If this thing happens, then that thing will happen. And then in the two cases where Maria doesn't sing, like, it's just always true. Yeah? Okay. Now, only if Maria sings, Javier will leave. Only if. So if Javier leaves and Maria didn't sing, then that's false, right? You're saying the only circumstances under which Javier will leave are the circumstances in which Maria sings. So now, if Javier leaves and Maria sings, then the conditional is true, right? If Javier leaves but Maria didn't sing, then it was false that the only circumstances under which he would leave are that Maria sings. Yeah? So is it clear why it flips it around, right? Yeah.
One of the two truth tables is wrong. I think the S implies X is that exactly the same.
Sorry, one of them is wrong?
Yeah, they're both true, false, true, true, but they're the opposite. One's S implies X, the other is X. But the third column is true, false, true, true.
The third column is true, false, true, true. Yeah, no, that's right.
But one's if X then X, and the other's if X then S. Oh, sorry, the columns are different. I'm sorry.
So,
I didn't realize.
oh, I see what you mean. Okay, yeah.
They were exactly the same, but never mind.
Okay, good. Whew. Okay. Hang on a sec. How much more do I have here? Okay, we're almost through this material, which is hilarious. So I propose typically if we're going to go I don't think we're going to go the full 2 hours. Typically, if we do, I would give you a break right now. But do you want to just plow on through? Okay. Was that one? There was one no. You can have a break. I won't be hurt. Just space out. Okay. Okay, so now I know that I can give you more examples. Yeah. Okay. So is it clear why only if flips this around? Yeah.
Could you go over the third case? Because we have Javier will leave, that's false. But we have true that Maria sings.
Yeah.
That statement true.
So on which side of this?
So, table 2,
Row 3. Okay, so this is the only if case.
Yeah.
So only if Maria sings, Javier will leave. Well, in the case that Javier doesn't leave, it's this conditional kind of just doesn't apply. So it becomes trivially true if it doesn't apply. This is so the second two columns of this.
What's the difference between only if and if and only if?
Okay, so if and only if is a slightly different case, right? So if and only if is when you have both if S then X and if X then S. So, like, honestly, I somewhat recommend not even trying to understand the third and fourth columns of this truth table because they don't make sense. They don't make sense. Fancier versions of the conditional, what's called the counterfactual conditional, kind of cut these out and say, well, instead of, so here we're saying, so in the third column here, we're saying, only if Maria sings, Javier will leave. Well, Javier didn't leave, so the question of what happens, what's the only case under which he leaves? Well, that doesn't even kind of apply here, right? Because he didn't leave. What I'm saying is not satisfying and it doesn't make sense because this conditional doesn't really make sense. Yeah.
So, I mean, it makes sense to me.
Oh, it shouldn't. I think you've got something wrong. Something's gone horribly wrong if it makes sense.
Okay, so because if Javier doesn't leave
Yeah.
and Maria sings, that doesn't say that So this says only if Maria sings, have her leave.
Right.
But the fact that he doesn't leave doesn't mean that that's wrong.
Right.
It just means that only when she sings, he can leave.
Right.
Whether he leaves
Right.
or not is irrelevant to that point.
Right, good. So it doesn't mean that. So it doesn't mean that it's wrong. So if you say, good. So this is what. Okay, but this is why it's weird. Saying it's not wrong in most cases doesn't necessarily mean it's right, unless you're doing formal logic when there's only two truth values available, right? So if I say I'm happy when it rains, if it's not raining, I haven't said anything about whether I'm happy or not, right? Confusions, questions? Yep.
Can we just understand it as if it starts false, it ends true?
Yeah. For the conditional, if it starts false, it ends true. That's the rule. That's the rule. I kind of just recommend that you just memorize this. Yeah.
It's like vacuous truth.
It's vacuous truth. Thank you. Yes. So it's like it's true because it doesn't apply.
Because you can't disprove it.
Yeah. We haven't in the
There's only two options.
yeah. In this case, it's true because we've defaulted to true because it doesn't apply. And here's why you have to default to true. If you made these both false, then the conditional would be the same as conjunction. This conditional would be the same as saying and, right? So if you say, here's the truth table for and. True, then it's true, and any other condition it's false, right? So if we got to pick either true or false for these things, right? There's only two options. We're not allowed to be like, oh, it's indeterminate. And if you made these both false, then the truth table for the conditional, the truth table for if-then statements would be identical to the truth table for and. So if you say, if those both said false, then saying if Maria sings, Javier will leave would be exactly the same as saying Maria sings and Javier leaves. And we want to be able to distinguish those things, right? You want to be able to tell the difference between if-then statements and statements, right? Yes. Logicians do, therefore you do too, by dint of being in this class. So that's why these two both they default to true. If it doesn't apply, we default to true. Because if you defaulted to false, it would be identical to and. Yeah?
Can you explain how this works with sufficient and necessary?
Necessary and sufficient. Can we do that? We will get to that. We will absolutely get to that. Can we not do that today? Is that okay? Okay. I want to. You've seen me in action. You want me prepared for that, so I don't flip it around in my head. Okay. Yeah. Hi. Yeah.
I just had a question about the previous slide.
Sure.
It says Xavier will leave if Maria sings.
Yeah.
The antecedent is the second part of the sentence.
Yeah.
So wouldn't it be X then X if the antecedent would be the second part of the sentence?
So this is precisely the point of showing you this, so that you know that it's not which part of the sentence. So the antecedent is not the first part of the sentence. It's the first part of the conditional, which is different. So these all still say that these are all still making the claim that if S is true, then X must be true as well, right? So that's what the conditional basically says, that if you've got S, if you've got truth value T for S, you must have the truth value T for X. That's still what these sentences say. So Javier will leave if Maria sings. That statement is true if, when Maria starts singing, Javier books it, right? So the fact that the antecedent comes at the second half of the sentence, like, it's still the antecedent even though it's at the end.
So would it make a difference where I place the S and the X, or does it have to be, like, does it have to be in that particular order? Because it means the same thing.
Where you place the S and the X when you symbolize?
Yeah.
Yes, it does matter. It does matter. Yeah. No, if you symbolize any of these sentences, so assuming that S means Maria sings and X means Javier leaves, if you symbolize that as if X then S, that would be incorrect. That would be incorrect. Yeah. So it does very much matter which order you put them in, because again, we're making different claims here. So if Maria sings, Javier will leave is a different claim than only if Maria sings, Javier will leave. So you can symbolize it one way, like, yeah. So you can write the sentence different ways, but you have to symbolize it this way. Okay. Yeah.
The last transition, if only Maria sing Javier
Yeah.
So if we put just if Mario says, if Mario doesn't see, Javier doesn't, will not leave.
Good. Yeah.
We don't need only the both the same.
Good.
Like in the last condition, the only doesn't do anything. If does it.
Well, it's not that it doesn't do anything. It's that there are multiple ways of getting something logically equivalent to this. Yeah. Yeah. So I think what you just described is something logically equivalent to only if Maria sings, Javier will leave. Yeah. Okay. Are we okay? Are we okay with this? Okay. I'm always a little worried when there's like whispering and murmuring, because it's either people who aren't willing to put up their hands and ask questions, or people who just hate the class and want out. Yeah, yeah.
I'm just still not super clear on why we have to flip it for only.
Right. Okay. So, if Maria sings, Javier will leave, is perfectly compatible with the case where Maria doesn't sing and Javier either leaves or doesn't. Right? So if you say, if Maria sings, Javier will leave, but if she doesn't sing and Javier leaves, that's still okay for your sentence, right? You haven't made the sentence false. Similarly, if she doesn't sing and he does leave, it still doesn't make your sentence false, right? So it's a case of what makes the sentence true or false. In the case of if Maria sings, Javier will leave, the only thing that makes it false is Maria singing and Javier hanging around. Yeah? So that's the only thing that makes that sentence come out as a false conditional. Now, the only thing that makes only if Maria sings, Javier will leave, the only case in which that turns out to be false is if Javier leaves but Maria doesn't sing. Yeah? The only case. So if Javier leaves, if Javier doesn't leave and Maria sings, that's compatible with only if Maria sings, Javier leaves, right? Similarly, if Javier doesn't leave and Maria doesn't sing, that's still compatible with only if Maria sings, Javier will leave. So there's only one case that falsifies both of those sentences, and it's a different case. Yeah? The case that falsifies if Maria sings, Javier will leave is Maria sings and Javier doesn't leave. The case that falsifies only if Maria sings, Javier will leave is Javier leaves, but Maria doesn't sing. Yeah? Yeah?
I understand what you're talking, but why does that mean that we will have to flip the accent as while we symbolize the sentence?
Well, because,
Is it because we want to satisfy this chart over here?
That's right. So this is the truth table for the conditional, right? So this is how you map the truth values of the parts of the conditional to the truth value of the whole sentence. And so this is the truth table that captures what you mean by if Maria sings, Javier will leave. And this is the one that captures what you mean by only if Maria sings, Javier will leave. Yeah?
And what's in the chart never changes.
That's right. So that's right. So these truth tables are like, that's the truth table for the conditional. It's always the truth table for the conditional. So this is kind of what the conditional means. Right? The conditional is a function that maps inputs to outputs, and this is always how it's going to map those inputs to outputs. So what changes is what you're plugging into these two inputs. Yeah? The first thing and then the second thing. Yeah? Okay. So far, so good? Okay. So a couple of rules for symbolization. There's going to be a bunch of them. We're going to layer rules on rules. So far, we're only dealing with negation and conditionals, so the rules are fairly straightforward. But not and fails to give a negation that applies to the smallest sentence that they are a part of. Okay, so what does that mean? Suppose P is Roberta calls, Q is Susan will be distraught. So the sentence, if we're going to symbolize the sentence, if Roberta doesn't call, Susan will be distraught. So if Roberta doesn't call, Susan will be distraught. So it's a negation and a conditional. Then we've got if not P, then Q, which is a very different sentence than not if P, then Q. The first thing says, the first thing is true in any case where, it's easier to talk about falsifying the conditional. So the first thing is false. If not P, then Q is false if Roberta calls and Susan's not distraught. Yeah? Whereas this thing is the negation of the whole conditional. The whole conditional is negated. So that's applying the conditional to the whole sentence rather than the smallest part of the sentence that it comes right after. Yeah? Okay. If that's unclear, honestly, this stuff will be clear through practice. You're going to do a bunch of practice on this stuff, and acquiring this as a skill is probably better than memorizing the rule. It does make sense of, if you understand how grammar works, this all kind of makes sense. Okay? Here's another one. Wherever if occurs, except with only if, that's our exception, the antecedent is the bit that comes right after if. So you remember we saw this, you can flip the order of the sentence around and you still have the same conditional. So we say the sidewalks will be wet as P, we say it rains as Q, then the sidewalks will be wet if it rains is if Q then P. Right, so the conditional comes right after the if, or the on the condition that, or any of the stylistic variants of if. Yeah? So far, so good. Okay. Some sentences, sorry, yeah.
So if, wherever if occurs, then students will come right after if. That means only if the part that comes right after only if is the consequence of that.
That's right. That's right. Yeah. So in any case but only if, the antecedent comes right after if. With only if, the consequent comes right after only if. Yeah? Okay. And if you've got if and only if, we'll deal with this eventually, the biconditional, then you can flip the antecedent and the conditional around. It doesn't matter what order they're in. Yeah? Okay, we'll get back to that. Okay, so some English sentences are ambiguous. Remember, we're going to hunt down and shoot the elephant of ambiguity. Here's how we're going to do it. So this following sentence is ambiguous. It's not the case that the dog will bark if the mailman comes. It's not the case that the dog will bark if the mailman comes. So that could be, if the mailman comes, it's not the case that the dog will bark. If M, then not D. Or it could be, it's not the case that if M, then D. So that English language sentence was ambiguous between two logically different readings. Yeah, yeah.
Why can't it be the dog won't bark and the mailman will come?
The dog won't bark and the mailman will come.
Because it seems like the same thing. It's not the case that the dog will bark. So in other words, the dog won't bark. The mailman comes.
I don't think if that, so it could be that that's logically equivalent, but this doesn't say that the mailman will come though, does it? So nothing in that, so it's not the case that the dog will bark if the mailman comes. On neither of those sentences do you get it given to you that the mailman is going to come. Could be Sunday or whatever. The complexities of the mail system are irrelevant. It's just the fact is that the sentence does not logically imply that the mailman is coming. Yeah?
And what about just saying the dog won't bark? Does that just seem unnecessarily convoluted?
That could be the motto for this class. That seems unnecessarily convoluted. But the sentence says more than just the dog won't bark, doesn't it? It's about what leads to what. right? It's a sentence about, so there's clearly a conditional in this sentence and there's clearly a negation in this sentence, and it's our job to figure out where both of those go, yeah? So what was the suggestion was you just say the dog won't bark? Well, if what we mean is this thing, then that's compatible with the dog barking but the mailman not coming, right? So if the mailman doesn't come, then maybe the dog will still bark, right? So the sentence is compatible with, so if you just say the dog won't bark, that means that there are no circumstances under which the dog barks, but that's not what this sentence is saying. The sentence is saying under the circumstances where the mailman does come, then the dog won't bark.
But you can still say the dog won't bark if the mailman comes.
That would be the opposite. Or no. So that's what this says. The dog won't bark if so the dog won't bark is the consequent, and then if the mailman comes is the antecedent. Yeah. So that's exactly what this says. Sorry. Yeah.
So we were given the rule that negation attaches to the shortest sentence.
Yeah.
So, like the atomic sentence, the dog will bark, the negation is directly attached to that. So
Okay.
either you couldn't get the second condition or that rule seems false to me.
Good. So the question was, if you didn't hear it, the question was, we were given the rule that the negation attaches to the shortest sentence. Now, the question is, what's ambiguous about this sentence is, what's the shortest sentence? What's the smallest? So it attaches to the smallest syntactic unit that comes after it, but it's not clear just from this what the smallest syntactic unit is. Yeah.
But what you just said is only true of natural language and not like the logic language, right?
That's right.
Be very clear.
In logic, it is very clear, and that's part of the reason why we want to do this logical stuff, so that it becomes clear. But the natural language is not always clear. So there do exist, as a matter of fact, ambiguous natural language sentences where it's just not obvious from just these words what the smallest syntactic unit is intended. So the person, if you said this sentence, you had something in mind for whether it was this thing or this thing, right? So you had I know how to parse this. When you say it, I know how to parse it, or you're writing it out. You know how to parse it. You know what you mean for the smallest sentence to be, but is not given to you in the language here. And that's one of the reasons why we want to do this stuff, because you can turn this ambiguous sentence into a logically clear, unambiguous sentence by using the formalism. So that's the goal here. Yeah.
So in the second case, just to be clear, the mailman doesn't come and the dog doesn't bark.
No. Good. So that would be slightly different. So this doesn't say the mailman doesn't come and the dog doesn't bark. That would be like not M and not D, which is logically distinct from this. Yeah? This says it's not the case that if the mailman comes, then the dog barks. Yeah.
So I'm just unclear if we should translate it into like logical sentences based off all possible interpretations by the rule of linguistics, or if we should just assume that the sentence is written by like the English natural language sentence is written by the rules of logic.
So in all of the tasks that I'm going to assign to you, we're going to do our very best not to give you ambiguous sentences like this. Or, so here's a tricky thing that I could do, or this is a thing that's been done on tests in the past. We say, I'll give you an ambiguous sentence like this and ask you for both. You say, I will say, this sentence is ambiguous. Tell me the two different ways that you could parse this. It won't be the case that I will give you an ambiguous sentence and then expect you to know what I had in mind. Or if I do that, then everybody gets the marks for whatever they write down. So no, we'll try our absolute best not to do that. I had more material. I'm sorry, I should have given you a break. We had more material than I expected. Okay. So is the problem here clear? Like this sentence doesn't. How to apply the rules to this sentence is unclear. It's just ambiguous what this sentence means. Yeah.
How would you make that sentence clear? Like if you were to disambiguate that?
That's an excellent question. I would use a comma. That's what I would do. So commas help distinguish where the, and, oh, you STEM people, listen up when you're writing. This is Okay, so commas help to disambiguate what the syntactic units of a sentence are. Yeah? So it's not the case that, comma, the dog will bark if the mailman comes. So that's saying it's not the case that this whole thing. Right? And then in this case, you see the negation attaches to the smallest unit, and you've indicated what you think the parts of the sentence are using the comma. Alternately, it's not the case that the dog will bark, comma, if the mailman comes. So it's not the case that the dog will bark if the mailman comes. So the commas disambiguate. So when you're looking at a sentence, when I've given you a sentence to symbolize, pay attention to where the commas are, because the commas tell you about the structure of the sentence. Yeah? And for the rest of your life, when you're writing things, use commas carefully, because that's how you disambiguate your sentences for people. Yeah?
If you're negating an entire conditional,
Yeah.
the most popular natural language style form is not the case at.
I don't want to answer a question about the which natural language ones are most popular. I don't know how people mostly use sentences. Yeah, that's a good question about like the distribution of sentences in natural language, but I don't think I have a confident answer for that. Yeah, it's a good question. It's a good question for linguists. Yeah, yeah. Okay. So when you're looking at sentences to symbolize, pay attention to where the commas are. The commas tell you how the sentence is to be parsed, how the sentences are chunked. Okay, real quick, I'm going to show you basic symbolization in Logic 2010, and I think that's it for today. So once again, I'm in parsing. What do? I say close, close. I go to symbolization. I click select, and I pick one of the things to symbolize. And I'll just delete all my work here. Okay. So to do a symbolization, here's how you do it. You go over the sentence and you right-click, and then you tell me what's the major connective here. So you're going to select the major connective. So if the sentence W is the Bruins win, what's the major connective of the Bruins fail to win? Negation. Negation. Now you could, if you should so desire, write out the Bruins win. So that once you get to more complex sentences, this might be helpful to sort of keep track in your mind of which parts are what. But you don't actually have to do that to get this done. You just right-click again. You go to atomic, and then you write down which atomic sentence fits in there. But notice you can't use the lowercase. The lowercase will tell you, oh no, that's terrible because I'm dumb. You need to use the capital letter. So capital W. Now we've symbolized the Bruins fail to win as not W. I check to receive my cookie. Oh, I did it right. Hooray, I did it right. Yeah? Yeah.
So can you just type in W, or do you have to go through?
Let me see. I can't remember, to be honest. No, you got to go down to atomic. Yeah, you have to do the right-clicky thing. Yeah. Yeah? And then I save, and then I submit. Is that fairly clear? How we're going to do that? So do you want me to do one more just for the sake of... Okay, so once again, you go over the sentence, you right-click. Ina will not fail to be chosen as campaign manager. What's the major connective of that sentence? Negation. So if you were like a reasonable person, you would see the not and the fail and be like, that's a double negation, so I can just go straight to the atomic sentence P. But that's wrong. Check that. Nah. We're going to be super duper picky, all right? What we're going to do is say that it's a negation of a negation of P. So Logic 2010 does not treat double negations as identical to just the sentence. So you need to include the double negation. Okay? Okay. So try those out, and we'll talk about derivations on Wednesday. Thanks, everyone.